Beat the first overflow challenge. Now overflow the buffer and change the return address to the flag function in this program. You can find it here on the shell server. Right, so we'll copy paste that again. Let's see what we have. So we have a vulnerable program, set UI or set group ID so it can read the flag when I can't. I have some source code. All right, so let's see. It's gonna allow me to overflow the buffer, and it's gonna tell me exactly where it is going. Let's see how big our buffer is. Our buffer is about 64 long. Okay, so if we say, looks like it reads this from standard input, so we'll say something like print so we'll print the alphabet. Before we print the alphabet, let's print like 64 A's. And then we'll, pipe that into the vulnerable program. All right, oh, put the wrong thing in quotation marks, right? So this Python program will do is it's going to do 64 times A. So I'll have the letter A 64 times, followed by the alphabet. The Python program will print that out. We'll pipe that output into the program vol. Okay, so whoa, we're jumping to 54F, 4E, 4D. So let's go to ASCIItable.com. And 50 is the letter P. So at PONM, so MNOP are the 4 letters that are going to end up in the return address. You'll see that it ended up backwards, right? PNOM. That's because the Intel is a little endian architecture. So the least significant byte is stored first, and then the more significant byte. So MNOP. So we need to replace that MNOP with the address of something useful. So if we do an obj dump on vuln, this is going to give me all the assembly code for the program vuln. So that flies by really fast. But what was really interesting for us is there is a method in here called win. They're called flag. And so if we call that flag method, then we win and we get the flag printed out. So I need to find the address of flag, and I need to put that in for the MNOP. So I'll do that obj dump again. I'll just grep it for win. No, not win, flag. So flag is at 080485E6. So if I go to my program at the MNOP, I replace it with the address of flag. And so I need to put the address of flag in little endian order, right? So the least significant byte first. So that E6, the /x is telling Python that this is a hex, a couple hex characters, which are going to correspond to 1 byte. Then 850408. So that should, if all goes well, put the address of the flag method for the return address. So then it will overflow, and so we look here. So it's going to write past the end of the buffer. On the Intel architecture, what's interesting is the place that the vuln method should go when it's done is stored on the stack. So we write past the end of buff, and we get to where the return address is stored. We overwrite that. We're overwriting it with the address of the flag method, and it should call the flag method. And then it's probably going to crash, right, because we have this QRST, which will be the address of garbage. All right, so it jumps there. It prints out the flag, and then it did crash, just as I expected. And so here is our flag.